Hello class, this is task number 2, and in this lesson we're going to be studying the Taylor series. If you remember from the last lesson, we learned about the power series, which was as I said, a series of or polynomials where it followed the order of x plus x squared plus x to the third plus x to the fourth. That was the power series. This one we're going to look at a different series. It's called the Taylor series. This over here, the person that found or invented the Taylor series, Brooke Taylor, musician, painter, dabbled in all this stuff, but he was more importantly, as it says here, he was more famous for what he found out about infinite series. So if you turn to the next slide, the point of the series is, what if you wanted to approximate, and again, like with a lot of these calculus stuff, I don't know why someone would want to do this, but this is what we have to study, is what if I wanted to find a polynomial that was in this form, looks like the power series, right? X squared, x to the third, x to the fourth. What do these numbers have to be that would make this very, very similar to this function at x equals 0? So essentially, what they're trying to do is, could they make something that looks like this but is in this format? So what you do is, if you can make p0 equal to f of 0, okay, and the first, the second, the third, and fourth derivatives are the same, if I take this and I take this and I plug in 0 for both and they're the same, and I do the first, second, third, and fourth derivatives and they're the same, then for all intents and purposes this function could be exactly just like this function. So let me show you how that works. So here on the next slide, you'll notice here on the left is that function that I want to create, and here on the right is the one I'm trying to mirror. So first of all, let me plug in 0 for both. If I plug in 0 into this one, I get ln of 1, which is 0. So that must mean that in this particular form, a0 has to be 0, because all this sort of disappears at x equals 0, right? So a of 0 has to be 0. Now let's take the derivative of both and plug in 0 again. So if I take the derivative of this one, if I take the derivative of this one, ln x plus 1, it is 1 over x plus 1. Okay? And if I plug in if I plug in 0, I'm going to get 1 over 1, which is 1. Good. Okay? Now if I take the derivative of this, if I take the derivative of this, I get this right here. And then if I plug in 0, all these disappear, which means a1 has to be 1 for these two to match. Okay? And lastly, I'll take the second derivative. You get negative 1 over x plus 1 squared. And if I plug in 0, I get negative 1. If I take the second derivative of my function that I want to create, I get this. And if I plug in 0, I get 2a to the 2. That means a to the 2 has to be negative half for me to get negative 1. Okay? And they continue on the same for doing it for the second derivative. Here's the third derivative. Here's the fourth derivative. And figuring out what does a2, a3, and a4, what do they have to be for the f of 0 and the p of 0 to be to get the same value. So hopefully you guys understand what's going on here. So, sorry, voice just cracked. So what happens is, if I plug in those a0s, a1s, a2s, a3s, and a4s, I find that when I plug them in, I get this, and when I simplify it and reduce, I get this function right here. And again, what they're trying to say is that I'm trying to get this to look, again, trying to get this imaginary function I'm going to create to look like this function. And if you plot it, this one looks like a parabola, and then ln of x plus 1 looks like this. But at close to 0, you may notice that it looks almost exactly the same. They match up so close, you couldn't tell which one is which at 0. And again, you may not in your lifetime understand why you have to do this, but there you go. Okay? So the polynomial has the form, and this is also true of the Taylor series, f of 0 over 0, f prime of 0 over 1, f double prime of 0 over 2, and these are factorial. So you remember factorial, like 2 factorial is 2 times 1, 4 factorial is 4 times 3 times 2 times 1. That's the sort of, that is the pattern that you notice when we created this function. The derivative over 1 polynomial, the second derivative over 2 factorial, etc., etc., etc. No matter what the original function was, no matter what you want to do, that pattern always remains the same. So the Maclaurin series, if I'm trying to match a function at 0, that is the formula. The formula is f of 0 plus f prime 0 x plus f double prime 0 over 2 factorial x squared over 3 factorial x to the third. So that series that we just generated, we actually generated the Maclaurin series. And that's if we want to match a function at 0. If you want to center the series and its graph, if you want to pick a different center anchor, you want to pick a different place to match the function, that is what is called the Taylor series, which we talked about. And instead of saying zeros, you see how these are exactly the same, but instead of zeros, I have x minus a, where a is where do you want to center the series. So if instead of looking at 0, I want to match at 2, just put 2's everywhere you see a. So that is the Taylor series. Just a couple of examples. Let's say, for example, I want to match up a function that looks like cosine x. Well, looking at cosine, f of 0 is 1, f prime of 0 is 0. So again, derivative, the derivative, going all the way to the fourth derivative. Again, the fourth derivative is, if I can match all the way to the fourth derivative, then I'm good. So I took cosine and derived it 4 times. Derivative 1, derivative 2, derivative 3, derivative 4, and plugged in 0 into all of them. Okay, and you see how they get 1, 0, negative 1, 0, 1. Okay, and then all they did, look at your Maclaurin series. Again, look at the formula here, and all they did was plug in those numbers everywhere you saw the f of 0, f prime of 0, whatever, and then they reduced it, and this is the exact function that if I wanted to match this one at 0 would look like this. And if you want to see how the graph looks like, if I put into my graphing calculator, if I put this in and I put this in, you'll see at 0 I have this nice curve that looks exactly like cosine. And the more terms that you add, you can get a closer approximation. So if I go all the way to the 10th derivative, the 20th derivative, this will look more and more closely like cosine. Again, you can also do the same for cosine 2x. So using what we know from, rather than start from scratch, we could use the function that we already know, which is the one that we just did. And you can just plug in 2x everywhere you see it. So that's another way that you can sort of use stuff that you already have and get the same answer and sort of speed up what you have. What if instead we say we want to mirror cosine, but not at 0, but instead I want to mirror cosine at pi over 2. Okay. So again, I'll take 4 derivatives of cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is sine. Derivative of sine is cosine. Plug in pi over 2 into all of them. They get 0, negative 1, 0, 1, 0. And again, they just plug it into the formula for the Taylor series. These are things that you're going to have to remember. Remember it was x minus a. So instead of a, I put pi over 2. Okay, so there's pi over 2, pi over 2, pi over 2. There's the factorials, right? And then they plug in on top the coefficients. So 0 goes here, negative 1 goes here, 0 goes here, 1 goes here, and so on and so forth. And when you reduce this and you take away, the zeros that don't matter, this is the answer for that. So hopefully y'all understand the Maclaurin and Taylor series. I know it's complicated. I'm teaching you over a PowerPoint on a video, but hopefully if there's anything you understand, it's that you're just taking or trying to create a function and trying to mirror a different function that already exists. And again, we may never use it, but that's what it's for. So you're gonna write. So the only assignment's gonna write a 3-sentence summary of what you just learned, what you understand, what you get about the Taylor series, and then I'll see you for the next video. Take care.